Welcome back to the Transformer series. In the previous episode, we built scale.product attention from ground up. We had queries that ask what each position is looking for, keys that describe what each position contains, and values that carry the actual content to be mixed. We computed similarity score, applied softmax to get weights, and produced a weighted combination of values. That mechanism is genuinely powerful. A single attention operation can learn to focus on a relevant position and build rich contextual representation. But it has a fundamental constraint that we have not addressed yet. A single attention operation produces one weighted mixture. When a single word in a sentence simultaneously needs to know who it refers back to, what grammatical role it plays in that clause, and what relationship it holds to words 5 positions away. One mixture cannot preserve all 3 signals cleanly, right? The most prominent signal dominates and the other get averaged down. A multi-head attention is built to solve exactly that constraint. The phrase on the screen captures that whole idea precisely. Different lens, same engine. By the end of this episode, every word in that phrase will have a precise technical meaning. Constraint we named with the spotlight analogy is not just intuitive. There is a mathematical reason for it. And that reason lives in how a single attention head represents information. Before the formula, let us see the problem visually. This is a single head, right? Attention head. Picture as one spotlight shining down on a sequence of tokens. The beam can swing across the sequence. At any moment, it assigns weights to different positions and blend their content into one pooled output. The motion you see is intentional. The spotlight swings because the attention weight shifts depending on the query. But at every moment, the result is the same type of thing. One weighted sum of all the values it can see. The constraint is not about where the spotlight points. The constraint is that there is only one spotlight. Everything is illuminated, get poured into a single mixture. Distinct signal that lives at different position get blended together, and what makes or what comes out other side is a weighted average. The sentence names the problem precisely. One weighted mix can blur distinct patterns into one average. The information is not destroyed outright, but it loses resolution. A strong signal at one position will dominate, and a weaker signal at other position will be present only faintly in the blend, right? For tokens that genuinely need 3 independent pieces of context simultaneously, one blend is not enough. Multi-head attention replaces the single spotlight with a lightning rig. 4 spotlight at each the same type and they uses the same type of lamp, each with its own filter and its own angle of swing. They run simultaneously and completely independent. What head 1 sees does not interfere with what head 4 sees. Their output are kept separate all the way through the computation until a deliberate integration steps which is at the end. The 4 colors are not for decoration. Each color represents a different projection of the input, meaning each had transformed the raw input through its own set of learned matrices before computing attention. That transformation is what makes each head genuinely different, not just aimed at different position, right? We'll make that precise in coming slides. Parallel spotlight at each learning a different view. The word learning is important here. Each head's projection matrices are trained parameters. They are not handcrafted to look at specific things. They emerge from gradient descent on the training data. The result is that different head developed sensitivity to a different structural pattern in the language, because that is what minimizes the loss. This sentence is from original paper. Read it carefully because every phrase is load-bearing. Jointly means parallel, not sequential here. Different representation subspaces means the projection before attention is different per head. So each head operates in a geometrical different region of the embedding space. Different position means each head attention weight can peak at different token. One sentence, three distinct claims, all of which we will now make concrete in the anatomy of a single head. The spotlight analogy showed us the parallel structure. We need now is the internal anatomy of a single head, because the spotlight analogy cannot show you the matrix multiplication that make each head see something genuinely different. The input X is on screen. Every row of X is embedding for one token. Every column is one dimension for that embedding. The shape is sequence length by d_model. Every head receives this identical X at its starting point. That is what same engine means. The raw material going in is the same for all head. 3 arrows are drawn from X to 3 weight matrices. The gold arrow curves up to gold box. That is the query projection matrix for head I. The cyan arrow goes straight to cyan box. That is the key projection matrix for head I. Teal arrow curves down to teal box. That is the value projection matrix for head I. Each of these 3 boxes is matrix of learned weight. They are different for each head. Head 1 has its own private set of all 3. Head 2 has completely different private set. Head 8 has a different set again. This is where different lens lives in the mathematics. The matrix reshape the input before any attention is computed. Head 1 query the projection point, the query vector in different direction in the embedding space. Then head 4 query projection. The 2 heads are not just looking in different direction, they are looking through genuinely different optical lens. The output of multiplying X by each projection matrix gives us the 3 head queries, keys and values. These you can call them Q_I, K_I, V_I, where the subscript I mark them as belonging to head I specifically. They are not the same as generally Q, K and V of full multi-head block. These are projected version that lives in the subspace created by head I on its own weighted matrices. Think of the color filter photograph analogy from the spotlight side. The room is identical in every photograph. What appears bright and what appears faint depends entirely on the filter in front of the lens. The filter here is the weight matrix. Head 1 and head 4 both start from same X, but after their respective projection they are working with representation what emphasizes completely different feature of the input. Once head I has its Qi, Ki and Vi, it runs exactly the scale dot product attention, the operation meaning query times k transposed divided by square root of dk, then softmax, then weighted sum with values. We have already seen this in previous video, right? The output arrow emerging on the right is the result. One contextualized vector per position in the sequence labeled head I. Follow the data flow left to right. X enters on the far left. 3 arrow split off to 3 weight matrices. 3 projected output feed into the attention engine. 1 enriched output exists on the right. The entire path is one head. The same operation runs in parallel for every other head, each with its own private weight matrices. Different weight matrices, same computation, producing a different view of the same input. This is complete anatomy of a single head. The next slide, write this as a formula and then ask what happens when each of these run simultaneously. The anatomy slide showed the mechanism as diagram. The formula is the same mechanism written in compact matrix notation. Regarding the formula in sequence give you the complete computation for one head in 3 lines. Step 1 is the projection. Qi equals to x multiplied by the query weighted matrix belonging to head I. Ki equals to x multiplied by key weight matrix belonging to head I. Vi equals to x multiplied by value weight matrix belonging to head I. 3 multiplication, 3 different weight matrices all starting from the same x. We know this. When more than one head is used, and we will work through the exact numbers in later slides, what matters right now is that the subscript I on every weight matrix mean these matrices are private to head I and numerically different for every head in the stack. The projection step we just read run independently for every one of H heads. The panel on the right makes this concrete. Head 1 computes its own Q1, K1 and V1 using its own 3 matrices. Head 2 computes its own Q2, K2 and V2 using a completely different set. Head 3 and all heads up to head H do the same. All of this happens in parallel, not in sequence. The computational cost scales linearly with H, but because d underscore k also shrinks by factor of H, the overall compute stay bounded. We'll verify this arithmetically precisely in the next slides. Step 2 is the attention computational step for head I. The formula reads as such. Head I equals attention applied to Qi, Ki and Vi. The attention function here is exactly the scale dot product attention from the previous episode. Dot product of Qi with Ki transpose divided by the square root of dk, apply softmax on it to get attention weight and then multiply it by Vi to get the output. Nothing in this step is new. The entire novelty of multi-head attention lives in step 1, the projection step. Step 2 is identical to the engine running on different fuel. That is the complete per head computation. Because the weight matrix differ across heads, the projected Q and K vectors point in different direction, which means the attention score will peak at different position for different head, which means each head pulls different content from the value, same operation different levels for different output. One head cannot represent 3 independent patterns simultaneously. H heads running in parallel can. Each head has now produced its output, one vector per position, shaped to be d underscore v dimension wide. We have h of these outputs and they need to become one representation that can be passed to the next layer. The question is how to combine them without disregarding what each head found. The operation is concatenation. Each block you see sliding in represents the output of one head for a single position in the sequence. The concatenation places them end to end in one wide vector. If h equals 8, then d underscore v equals 64, then each head contributes 64 dimension and the concatenated vector of 8 times 64, which is 512 dimension wide. All 8 views are present, packed side by side, with no information discarded yet. The concatenated vector cannot go directly to the next layer for 2 reasons. The first reason is shape. The next layer expects d underscore model dimension, not h times d underscore v dimension. The second reason is more important. Simply placing 8 vectors next to each other does not tell the model how to weight or blend their contribution. We need a learned integration step. That is what multiplication by WO provides. WO is output projection matrix. It has a shape h times d underscore v by d underscore model, which means it projects wide concatenated vector back to the standard d underscore model width. Critically, output projection matrix, which is WO, is trained parameter. During training, it learns which combination of head output are most useful for the task. A head whose projection matrix align with the most relevant pattern will have its contribution amplified by the output projection matrix. A head that is redundant for the current input will be downvoted. The integration is not averaging, by the way. It is learned combination with full capacity to favor any subset of the heads. This is the complete formula. Multi-head of QKV equals to concatenated of head 1 through head H multiplied by output projection matrix. Every term now has a mechanical meaning you can trace. The head comes from per head projection and attention operation we built on the previous slide. Concatenate them or join their output side by side, multiply them with the output projection matrix and project the result back to D model dimension and learn how to blend it into parallel view. One formula for operation: project, attend, concatenate, integrate. The formula tells us what happens. This slide explains why it produces better representation. The key claim is on the screen. The real advantage is not that the head look at different word positions. The real advantage is that the head operate in different representation subspaces, and the consequence of that is profound. Start with a single head case. Imagine three distinct structural patterns that model needs to represent for a given token. A co-reference link highlighted in gold, a syntactic dependency in cyan, and a positional boundary in teal. One attention head produces one weighted mixture. All three patterns flow into the attention. Basically attention computation. Together, that too. That comes out in the grey bar at the bottom. A blended average signal. The gold is there, but it has been mixed with cyan and teal. None of the three are in full strength. The single head has made a trade-off it was never asked to make. The sentence on the screen is precise. Distinct relationships get mixed into one representation and information is lost. This is not a theoretical edge case, it is a real limitation. Whenever a token simultaneously participates in multiple independent structural relationships, the model could in principle allocate all its capacity to one pattern and ignore others. But then it would be representing only one of the three at any given time, not all three simultaneously. Multi-head attention provides 4 independent streams running in parallel. Each stream operates in its own subspace, which means each one can develop sensitivity to different structural patterns without interfering with others. Head 1 might specialize in co-reference. Head 2 might specialize in syntactic roles. Head 3 in maybe positional proximity, and Head 4 in a long-range context. The gold stream does not depend with cyan stream. It does not blend with cyan stream, at least at this particular stage. They stay separate all the way through concatenation. Each stream is preserved intact, which is the whole point. The mixing only happens at WO, which is output projection matrix. The output projection matrix is a learned matrix that can decide the right way to integrate them for a specific task and input. The model is not forced to choose between the three patterns. It can represent all three simultaneously in separate streams and then learn how to combine them. One important calibration before moving on. You will often hear claims that individual head learn specific roles. A syntax head, a co-reference head, a positional head. Probing experiments do find structure patterns in specific trained models, and those findings are interesting, but they are not design guarantee. The projection matrices learn whatever helps minimize the training loss, and the pattern they develop depend on the data, the task, and the specific architecture. The claim this video make is the one on the screen. Heads increase the model's capacity to represent multiple interaction patterns simultaneously. That claim is true by design. Whether those patterns align with human linguistic categories is an empirical question about a specific model. The mechanism now is fully explained. What remains is to watch it run on a concrete sentence. and see that a forehead produces genuinely different attention pattern, not just noisily different version of the same one? The sentence is, the doctor said he would help. The token we are watching is he, highlighted in gold because it is performing the query role. Each head constructs a different projected query vector for he and then compute similarity with the projected key vector for every other token. The head whose projection matrices make he most similar to specific token will draw the strongest arc to the token. Okay, let's see what happens. Each attention head is its own parallel channel. Every head has a separate Q, K, V projection, different weighted matrices. So each head operates in a different subspace and can latch on to different kind of relationship. What you are seeing is a learned behavior, not a hard-coded rules. When a head looks at coreference sensitivity, that description of the pattern is discovered during training, not something it was explicitly designed to do. Heads don't overwrite each other, they accumulate. Multiple heads can attend to different tokens at the same time, and their contribution are combined later. One head attention doesn't erase another. But why multi-head attention is stronger than single-head attention? One token, in this case he, can simultaneously need multiple structural signals: entity reference, governing verb, future action, long-range dependency. A single head would have to blend these into one attention distribution, which will be weaker and muddier signal, right? Multiple heads keep these signals separate and sharp and then merge them. The net takeaway is multi-head attention let model represent several different relationships. Now, the four head output are concatenated, so view 1, view 2, view 3, view 4 are placed side by side. The output weighted matrix that we get, is basically a projection matrix of the output, is then produced a single vector for the token he that holds all four type of contextual information at once. That enriched vector passes to the next layer. This is exactly what we said a single head could not do. One head would have blended all four signals and in the process lost resolution on each one. Four head kept them separate. So WO integrates them with a learned weight. A natural question after seeing four head run in parallel is whether the computational becomes 4 times more expensive. The answer is no, and the reason is in the dimensional formula. This slide shows exactly why multi-head dimension is as efficient as it is. The formula is dk equal to dv equal to d model divided by h. The per head dimension is full model dimension divided by the number of heads. Each head does not get the full d model width. Each head gets d model divided by h width slice of it. The total dimension budget is fixed. It is divided equally among all heads. This is what split the model dimension means in the slide heading. The head are not doing extra work. They are dividing the existing work into smaller parallel pieces. The concrete numbers are such. So d model equal to 512, let's suppose, and h equal to 8. Dividing 512 by 8 gives you 64. A full width 512 dimension bar is on the screen representing what a single attention head would work with. All 512 dimension in one stream. That is the baseline. Now 8 times 512 is 64. The 8 small bar together cover exactly the same total dimension width as the one big bar. But instead of one stream working with 512 dimension, you have 8 independent streams and each working with 64 dimension, each with its own projection matrices. The computational cost of attention scales with the square of sequence length and linearly with the dimension. When you cut decay from 512 to 64, each head attention metrics become 8 times cheaper. Running 8 such heads simultaneously bring the total cost back to roughly the same as one full width head. The representation capacity increases because each stream specializes independently. The wall clock cost stays bounded. This is the elegance of the design. Understanding the efficiency of multi-head attention makes it easier to appreciate why the original transformer used it 3 separate times in each layer. Each use has a different purpose, and understanding all three makes full architecture legible. The first use is in encoder self-attention. Every input token attends to every other input token with no restriction. The query, the key, and the value vectors all come from the same set of encoder input embeddings. Every position can see every other position in both directions, before and after in the sequence. By the time a token exists, the encoder stack, its representation reflects full bidirectional context of the input. The second use is in decoder masked self-attention. The decoder also runs self-attention on its own sequence, but a casual mask is applied to a raw attention score before softmax. Any position in the sequence can only attend to position that comes before it. The question mark in the box represents future positions that are blocked. This masking is what makes auto-regressive generation possible. When generating token, a position at position t, the decoder cannot see tokens at position t+1 and beyond, which prevents it from cheating by looking at the answer during inference. The third use is in encoder-decoder cross-attention, and this is the bridge between the two halves of the transformer architecture. The query comes from the decoder current state, representing what the decoder is trying to generate. The key and value comes from the decoder output, representing fully processed input sequence. Through this cross-attention operation, the decoder can consult the entire encode input at each generation step, which is how a translation model learns to attend to a relevant source of words while producing each target output. All three applications uses the same formula: project, attend, concatenate, multiply by the WO, right? The only thing that changes between them is where the query key value comes from. Encoder self-attention, all three comes from encoder input. Decoder mask self-attention, all three from decoder input with casual masking. Cross attention, query is coming from decoder, and key and value is from the encoder output. One mechanism, three distinct roles in the architecture. The three-place structure of the transformer show how extensively multi-head attention is used. Natural follow-up question is whether more heads are always better. The answer is no, and the formula we already derived tells us exactly why. Watch the bar grow in sequence and note the shape of this curve. Going from 1 head to 2 to 4 to 8, the performance rises. More head and more independent subspaces means more capacity to represent diverse pattern. But between 8 and 16, the improvement sort of stalls, right? At 32, shown in red, performance has dropped below 8 head peak. The dimension formula explains this precisely. If the dimension of the model, D model, is 512 and H is equal to 8, gives dk equal to 64 per head. Now, if H is equal to 16, dk becomes 32. If H is equal to 32, dk becomes 16. A head with only 16 dimension to project into has a very limited capacity to learn a meaningful structure pattern. You have added more spotlight, but each one is too dim to illuminate anything clearly. More heads, smaller decay per head, and eventually diminishing total capacity. The two statements on the screen are the complete lesson. The left one is the mechanism. More head means smaller decay per head, and each head is therefore less expressive. The right one is the practical consequences. Number of heads is a hyperparameter you tune through experimentation, not a value you simply maximize. The original transformer paper used 8 head with demodel dimension equal to 512. Gives decay equal to 64. Large model use different values because demodel is larger, right? And optimal trade-off between head count per head dimension shift accordingly. The mechanism is fully explained. Before the closing slide, here are 5 questions that probes whether you can reconstruct the material from memory. Pause the video after each question and answer it in your own words before reading the answer. If the answer requires you to look back, that is the exact concept you want to revisit. What is an attention head in one sentence? The answer is the same scale.product attention with its own learned projection metrics for queries, keys, and values. If your answer focused on which token a head attains to rather than on the projection matrices, you want to look back. The projection are the mechanism, the attention pattern are just results. Why two head have different projection matrices? Because each head needs to operate in a different representation subspace. Without different projection matrices, every head would compute identical query, key, and value matrices from the same X and would produce identical output. They would be computationally expensive duplicates, not parallel views. What does the concatenation plus WO step achieve? Concatenation places all heads output side by side into one wide vector. The output projection matrices projects the vector back to D-model dimension. Using learned weights that decides how to blend each head's contribution. This is not a shape matching operation. WO is a trained parameter that learns the optimal integration of the parallel views for a task at hand. Where does the multi-head attention appear in full transformer? 3 places, right? Encoder self-attention, decoder mask self-attention, and encoder-decoder cross-attention. Why is more head not always better? Because dk equals to d model divided by h. Increasing h reduces decay, and a head with a very small decay lacks the capacity to learn a useful projection. Diminishing returns sets in and performance peak at some intermediate head count. The phrase on screen is the anchor for this whole episode. Different lens name the projection matrices, query metrics, key metrics, value metrics for each head. All different, all learned, all reshaping the input into a different subspace before any attention is computed. Same engine name, the scale.product attention computation that every head shares without modification. Together, the two phrases describe the complete design. Multiply representational capacity by running H attention operation in H different subspaces. Keep the computational cost bounded by shrinking each head's dimension proportionally, and integrate the parallel output through a learned WO that knows how to combine them. In the next episode, we stop looking at individual operation and assemble the full encoder block. Multi-head attention feeds into a residual connection, then layer normalization, then a position-wise feed-forward network, then another residual and another layer norm. You will see why that pattern of skip connection and normalization is what makes it possible to stack dozens of encoder layers without training instability. Those details are in next episode. If you like this series, do subscribe. See you in the next one.